Okay, let's dive right into this explainer. I want you to take everything you think you know about how a qubit works and literally wipe the whiteboard clean. Seriously, just erase it. Today we're drawing a completely new map. It's going to be a warm, beginner-friendly picture, no jargon, just pure understanding. We're looking at the hidden map of a qubit, something called the Bloch sphere, and trust me, it is absolutely going to change how you visualize quantum computing.
First things first, we've got to debunk this super popular, kind of confusing cliche. You've heard it, right? A qubit is a 0 and a 1 at the exact same time. People love saying that, but it makes it sound like the state is just some sliding number trapped on a line between 0 and 1. Nope, that is not it at all. A qubit state isn't a simple sliding scale. It actually takes an entire three-dimensional globe to pin it down. And honestly, once you can picture that globe in your mind's eye, the rest of quantum computing basically turns into basic geography.
To put into perspective why this mental map matters so much, think about the sheer stakes here. We're talking billions of dollars. Engineers are spending absolute fortunes right now just trying to control these tiny devices. They're cooling chips down to near absolute zero, they're firing wildly calibrated lasers at single atoms, and the entire point, the whole reason for all this incredibly expensive machinery is just to grab this fragile little quantum state and steer it exactly where they want it to go. If you don't have a map of where it can go, quantum algorithms just read like static and noise. But with the right picture, it's like having crystal clear GPS directions.
All right, so idea one, the globe. Plotting the compass arrow. Let's start building that globe together. Picture a tiny compass arrow just floating dead in the center of a 3D ball. We are not talking about your standard flat compass that only swings around in a circle. Think of a free-floating arrow that can point literally anywhere in three-dimensional space. Up, down, sideways, you name it. That arrow right there, that's your qubit. And the single fact that captures everything about its state is just asking, which way is it pointing?
Let's plan a couple of recognizable landmarks on this map. If the arrow points straight up to the North Pole, we call that 0. If it points straight down to the South Pole, well, we call that 1. And here's the kicker. Those are the only two answers you will ever get if you force the qubit to commit during a measurement. It literally has to pick a pole the second you look at it.
Now, physicists actually have specific terms for this globe and the arrow. The globe itself, that's the Bloch sphere. And that free-floating arrow pointing to your exact spot is the Bloch vector. I know I said no jargon, but this terminology actually proves a really crucial point. It shows that the state is a specific physical address in 3D space. It is absolutely not just some numerical slider stuck between 0 and 1.
Okay, this is the part that might just break your brain a little bit. The qubit isn't secretly hiding at the North or South Pole just waiting to trick you. While it sits there untouched, before any measurement happens, it genuinely is that tilted arrow pointing off somewhere toward the equator. It's leaning partly toward 0 and partly toward 1. And that lean, that exact direction, is its true state. It's not hiding as 0 or 1. That hard 0 or 1 only springs into existence the exact instant you measure it.
Moving on to idea 2, 2 dials, navigating the sphere. So how do we actually describe a direction on this globe? Well, it's the exact same way you'd pinpoint a city on Earth, with latitude and longitude. Our qubit's arrow is actually controlled by 2 invisible dials that work exactly like those geographic coordinates.
What's really fascinating here is how beautifully simple our controls are. Dial 1 is the tilt. It acts just like latitude, controlling how far down the arrow leans away from the North Pole. Dial 2 is the spin, which acts like longitude. Once the arrow is tilted, this spin dial controls how far it rotates around the equator. So yeah, just 2 simple, hand-drawn dials.
Let's take a closer look at that first dial, the tilt. This dial basically controls your betting odds. If the arrow points straight up, you get a 0 every single time. But if you use the tilt dial to lean that arrow exactly down to the equator, boom, you got a perfect 50-50 coin flip between 0 and 1. And if you keep tilting all the way to the South Pole, it's pure 1. So latitude literally sets your betting line.
But what about dial number 2? Spinning around the equator doesn't actually change those 50-50 odds at all. No matter which way you face on the equator, it is still a coin toss. So what does the spin dial do? It sets the phase. Phase is this crucial hidden gear that powers quantum interference. It's how quantum possibilities act like ripples on a pond, either reinforcing each other to build the right answer or entirely canceling each other out to eliminate the wrong ones. So here's the absolute wild part. This phase dial, this longitude spin, is completely invisible if you just measure the qubit once. Seriously,
Two qubits pointing in totally different directions around the equator will look completely identical. They'll just look like a 50-50 blur if you only look once. And yet, this hidden phase is exactly where the entire superpower of quantum computing hides. The most powerful setting on the whole machine is the one you can't even see just by looking.
You might be wondering, why do we only need exactly 2 dials? Usually finding a direction in 3D space takes 3 numbers, right? Well, the length of our arrow is permanently locked. It points, sure, but it never stretches or shrinks. And because that length is locked in place, we've basically spent one of our numbers up front. That leaves us with a budget of exactly 2 angles. 2 dials is the whole shebang. That's all it takes to map the entire universe of a single qubit.
All right, on to idea 3. Turning the globe, the quantum magic trick. Let's see how all of this beautifully comes together. This is the big payoff. This is the real quantum magic trick that translates the punishing, textbook algebra of quantum mechanics into simple, intuitive physical motion that you can actually picture in your head. If you ask what a quantum computer actually does, textbooks will hit you with a terrifying wall of matrices and complex numbers. But look at what that math actually means on our drawn-out globe. Every single complex operation is literally nothing more than rotating this arrow to a new direction. Flipping it from north to south, that's your basic knot operation. Tilting it from the pole down to the equator, you just created a superposition. Spinning it around the equator, you're just dialing in the phase.
The fearsome algebra and rotating the arrow on our globe are literally the exact same thing, just wearing 2 different outfits. Anything a supercomputer can grind out with matrices, you can picture by simply grabbing the globe and giving it a spin. We are taking incredibly hard math and turning it into hand motions.
Let this stop you cold for just a second. Deep down, an incredibly complex quantum program is nothing more than a dance. It completely collapses into this precise choreography of spins and flips, all applied to an arrow on a sphere. The entire exotic field of quantum mechanics suddenly becomes something you could almost mime with your own hands. How cool is that?
Okay, where we landed. A recap of the map. Let's quickly wrap up this explainer and review the beautiful, simple whiteboard map we just drew up together. We've thrown out all those confusing sliders and built something so much more useful.
We covered 3 massive ideas today. First, a qubit state is an arrow pointing anywhere on a 3D globe. It is definitely not a number trapped between 0 and 1. Second, we use 2 dials to aim it. The tilt sets your measurement odds, while the spin sets the hidden phase that drives interference. And third, every intimidating textbook equation you'll ever see is actually just a simple geographic rotation of that arrow.
So we've built the map, but how do we actually drive on it? Next time, the quantum gates. We'll open up the quantum toolbox and look at these specific, named turns, the quantum gates, that act as the actual verbs of computation. We're going to see exactly which spin does which job and how chaining them together lets us travel across this map to solve some very real problems.
But before we do that, I really want to hear from you. Which quantum idea has always felt like a total fog to you? Let me know in the comments down below. Is it entanglement? Is it measurement? Interference? Seriously, tell me. And we might just take that exact topic and turn it into a clear, hand-drawn picture in our next explainer. See you then.